You grind them.
I got it.
No, just got a laptop. It's a Surface Pro. This device.
I think it's $90.
$9. You can charge it.
Yeah, you can
It's
try
a
it.
USB.
No, it only has like this one. What do you call it? Backlight.
So it just sticks out like that.
Yeah, it's so annoying. So
Oh,
every
you
time
have
I-
it too? Picture. No. You have a pen? No. Yeah, at least you don't have to have a pen like that. Let me see. Because I have one
This
of
one
those.
is a lot better.
This is a battery. That's okay. It's what mine is. I'll be there.
Oh,
What is that, a quadruple A battery?
no.
That's not, that's not such. Holy shit, that's weird.
All right, let's go ahead and get started with a very quick lecture where we're just going to talk mostly about the final, a little bit about Fourier analysis, and then about the take-home final. We'll go through an examples kind of step by step so you can kind of try to put into context all the stuff that I sent you last night. So first things first, final exam next Monday. So cover 379. So upstairs and 3 to 6. Hopefully it will not take that long. Since we're doing part of it take home, we're going to have a reduced in scope final. So what the last exams were like 5 problems. So if you hadn't had a take home final, that'd probably be 10 problems. But since you have a take home final, that'd probably be on the order of 7, I think. And if I can make it smaller, well, if we can get it to 7 or 6, it's certainly going to be a maximum of 7 problems. Normal rules, no electronics, no closed book and notes. Oh, another thing, several of you have conflicts with other courses that are taught at the same time and have a final at the same time. If you do, just go ahead and complete that final and come to this room and go ahead and take it afterwards. So I'm hoping that everybody that will have this room from 3 to 6, maybe longer, and this final won't take as long. So if you're in that boat, and I know some of you are, I think I know David is, but if let me get a list. Send me an email with your name, so I will not leave the room and go home and leave you finalists. I know there's 19 finals, but help me help you. So make sure I know who you are, so I get a good count, and we're all accounted for. Okay, closed book and notes. That's normal. Any required tables we provided. So that's all the properties, a table of Z transforms, a table of Fourier transforms, and we talked a lot about windows and the side lobe levels of windows and the main lobe width, null to null. Those will all be provided. So you just know how to use them and what they mean. I will put them on the final because I don't think you need to have that on your pieces of paper. So though it's closed book and notes, you get 2 8.5 by 11 sheets of paper for notes, front and back are allowed. Topics. Well, it's the entire course. It's fair game, but clearly Z transforms and LTI systems are a pretty important part of the course since they're fundamental to everything that follows. Changing sampling rates by a non-integer factor is also pretty fundamental. The multi-rate signal processing and polyphase decomposition are pretty important topics. The structures are pretty straightforward. Those are just things you can kind of copy down. Partial fraction expansion. So that's an important one because you can use that for Z transforms or for the structures when you're trying to get parallel form. Filtering is a big one. Obviously, you're going to do a take-home final on filtering, so to some extent, that'll probably be mostly covered by the take-home final, but you still need to understand these terms, the pass band, stop band, transition band, know how to sketch the filters. Anti-aliasing filters, pretty important topic because if you can't get that right, then none of this stuff matters. You might as well just take the take the knowledge and chuck it if you have worthless data. So that's a critical topic. Without that, the data, there's garbage in, garbage out, right? DFT, the properties thereof, and I think apparently we had one tricky test problem on properties, so that probably gives you a feeling for the type of property type problems we can have. Linear and circular convolution, so the key parts of that was, what do we use circular convolution for? Not really anything that I know of, but it's usually a desperate attempt to get to linear convolution that failed. So we use linear convolution because that's the output of LTI systems. That's useful. It's like the output of filters or correlation receivers and communication systems, what have you. How do we implement that? DFT is an efficient way, but the DFT uses circular unless you pad it out to the right amount so that the circular is the same as linear. And so that was one of the major themes of the last exam. Block convolution, overlap add, overlap save. So there's just two algorithms that hopefully you can kind of go through the examples I put in the back of the, I think there's a lecture on that, and you can kind of see how to do it. So a possible exam question would be, given an FIR filter that might be A, B, C in an input sequence, what can you divide it into sections? What would the sections be given that you have to use a DFT of length 8 or something like that? So that'd be a type of fair question. Decimation in time DFT, decimation in frequency DFT. So what do I mean by that? Well, we talked about the two algorithms where one's in place. I guess they both have in place computations, but you have a bit reversed order depending on which algorithm you use for inputs and outputs. And remember, we put them kind of back to back so we could use them effectively. And remember, there was the beginnings of the derivation of the decimation in time is where you took what? You took the even part of the input data and the odd part and processed it separately. And then you could cascade it on down and make the decimation in time DFT was making one big DFT out of a lot of little DFTs. And you could do the same thing by starting in the frequency domain and taking the odd frequency samples, the even frequency samples, and kind of working the same way.
Is that the end modulo?
Yeah, that was that problem that kind of ended that way, where it was like, well, how come this is it was an endpoint, a 2 endpoint DFT, but we had these sums of a regular endpoint DFT. How to interpret that? And the interpret was, as you said, it was modulo n, but k went from 0 to 2n minus 1. If I'm that first problem. Yeah, that first problem. So if you're imaginative, you can think, well, we had the silly problem where we took the odd samples of the input and made them 0, right? In a sense, we took an n-length sequence, 0 padded it to make it 2n. So we did it with the odd. We could do it with the even, or we could do decimation of frequency. I mean, so that's the kind of things I want you to think about in terms of, feeling prepared to answer a question on that. So you can put that kind of stuff down on your sheet of paper. And then Fourier analysis and the effects of windows. And we're going to talk a little bit more about that today because I don't think last lecture quite answered the mail on all of that. But the Fourier analysis is, well, what I guess, given a certain length sequence, how can you resolve two frequencies given a certain record length of data, which we're going to talk about today, and the effects of the windows if they're too close together or too far apart. I guess not too far apart, but if they're too close together and the dynamic range of the dynamic range between the two signals is very large, like you have a very small signal next to a very powerful signal, will the side lobes of the powerful signal mask the smaller signal? I think we went through one example last time, but that's sort of the things we're going to talk about a little bit today. So Let's see what else we have here. I think that's it. So any questions on the final? Alright. I think what we'll do is do a very quick kind of recap of the Fourier analysis and finish that. And then we're going to talk about the take-home final. So this is a pretty quick lecture just to finish off Fourier analysis. So last time, someone asked the question about what's the relationship between the main lobe width and the frequency resolution, and I think I wanted to make sure we get all that squared away today. So window length, and that's the way the book likes to talk about it. I usually think of it as data record length, like how long did we collect all this data, how many samples, and how long did it take to collect it. And if we put a rectangular window on it, then there's not really any weighting at all applied, or hamming. Then we apply some weights or tapers, if you may. And we went through some of this stuff, and we said, well, these window lengths are proportional to the main lobe width. And in particular, in the text, we say, what is the main lobe width? It's the null-to-null main lobe width is the one they're interested in. And that's fine. Well, the main lobe width is proportional to frequency resolution. And frequency resolution is how close can two signals be together before that you can't tell that there's two signals. You think there's only one. Now, if you really want to solve this problem right, you have to get into the SNR of the signals, and you have to get into a statistical treatment of this. But we can start to begin to understand the main concepts in a non-statistical manner. And then it'll be a lot easier when you learn the statistical manner, because you already have these under your belt and you understand the relationships in play before you get into wrestling with the statistics of it. So let's talk about this. Main lobe, we know window length is going to be proportional to main lobe width. We talked about the windows, and we're going to talk a little bit more about it in terms of time today, and not just, oh, it's a rectangular window, oh, it's a Hamming window. We're going to talk about it in terms of time. And we're also going to talk about main lobe width is proportional to frequency resolution. So what do we mean by that? Well, there's different ways, different standards for frequency resolution. So one standard, so we could say one standard for frequency resolution this is the one the book uses, is null-to-null width of the main lobe. So let's sort of sketch a situation like that. So we've got one signal. And what I really want to do is make another signal. And so imagine that these signals are superimposed. So they're together. And I'm not drawing them superposed, I'm just putting them on top of each other, the blue signal and the red signal. And what do we talk about when we talk about the null-to-null main lobe width? Well, it's these first nulls. So this distance here is that null-to-null width, which of course it's the same for both signals because they have the same time support, the same number of samples, the same window, the same everything. So as it turns out, we can say, well, we're going to count it as we can resolve these frequencies. This is obviously two frequencies if they're separated, the centers are separated by the null to null width. Right, so here's the two centers. And there's half the main lobe width, there's the other half the main lobe width, so that is also the null to null, if I can write width, main lobe width between those two. And that's one standard. So that's basically someone saying, yes, I have an algorithm, some kind of means, a person with a stick who hits a green button when they see it, whatever, that says I can resolve these two signals because they're at least this far apart. Now this is a very conservative measure using the main lobe width. Many people use the 3 dB width, which we'll talk about next. So I would say this is a very conservative, sort of easy to detect case. If you want to use that criteria. And hopefully you can kind of see, yeah, it's pretty easy to see those are separate because there's a huge gulf that could be many dB down there. So if you had a simple algorithm that was trying to find, peaks between signals, it could probably find that. One useful criteria. The other criteria would be the other standard, or another standard, 3 dB main lobe standard. What do we mean by that? Well, if I had some frequency response that was 0 dB, and that's minus 3 dB down from the peak, then that width there is the 3 dB main lobe width. So what does that mean if we decide to cache that out in terms of, let's redraw our red and blue signals again, but this time let's put them so close together that they meet the frequency resolution standard of the 3 dB main lobe. So if we do that, one signal and then the other, I think I want to try to overlap it. So now if we had these centers, you can see from here to here is half the 3 dB main lobe width. From there to there is the other half. And that distance there is the 3 dB main lobe width. And that's another standard of frequency resolution. So you can see this would be a little bit harder because some kind of algorithm or some method that you may have to figure out if there's two signals or one is going to have to be more discriminating. It's not going to be quite as easy. Clearly, the farther apart these peaks are, the easier they are going to be to discover and characterize. So this is a slightly more difficult standard. So harder to detect, or I guess resolve. So, well, what's the payoff? Well, many times in many applications, you want to be able to resolve these frequencies. So saying that you're able to do it is good. And as we're going to see in just a moment, it usually costs money and time to gain resolution. So let's kind of start unpacking that a little bit. So before we talked about this rectangular window, and we mentioned, oh yeah, the main lobe width, this was null to null, was approximately, according to what the text said, 4 pi over m plus 1. And this is in normalized units, right? So it's radians. This is in the frequency domain. This is little omega. So if we plotted the spectrum in radians, little omega, and measured the null to null width, we would get 4 pi over m plus 1. Where, if you recall, this thing was parameterized, so it's all ones. From 0 to m minus 1, or is it just 0 to m? I think it's just 0 to m, sorry. 0 to m, and it's basically 0 otherwise. So if we were going to sketch this and say, let's let m equal 10, what would we get? Well, we'd get something like this, and according to our properties here, this null to null width is 4 pi over m plus 1. M is 10, so that's 11. And this is omega, which is in radians. So far so good. But now let's sort of turn this back and stop playing in the discrete time, frequency world, and go back to the normal time-based world, continuous time. And we'll do that by kind of a walk down memory lane where we recall, oh yeah, little omega is a scale version of the continuous time big omega, where t is what? The sample period of any sampling. Right. So let's remember what big omega is really just 2 pi times f, where f is the frequency and t is the sample period. So if we solve for f, just divide omega by 2 pi t, right? So there we go. So let's suppose we wanted to convert our frequency resolution in this discrete time frequency domain into regular time, or regular time domain continuous time, where we're using f, which is in hertz. So now the frequency resolution will be converted to hertz, which is something that probably makes more intuitive sense. So let's say the frequency resolution, or del f, is going to be what? Well, it's del omega, which we know, all over 2 pi t. What's del omega?
Circle.
Oh, sorry about that. Kind of got lost there. So omega over 2 pi t resulted in del omega over 2 pi t, where del omega is what? It's this main lobe width. It's this frequency resolution, kind of calling it a delta. It's the distance. So that's 4 pi over m plus 1. So 4 pi m plus 1 times t times 2 pi, which if we divide that out, we'll get 2 for m plus 1 times t. Well, this m plus 1 times t is really very close to the amount of time it takes to get all the samples collected, right? So I'm going to call a new variable collection time. Tau is going to be m plus 1 times t. Now I think, strictly speaking, if I had to collect 5 samples, I can count the spaces. That's 1, 2, 3, 4. So it's kind of be 4 times t, I would think, but for the entire collection time. But this is very close to the collection time. It's maybe off by one sample longer. So if we want to look at the frequency resolution in terms of this tau variable, it's just going to be 2 over tau. And that is frequency resolution in hertz. And this is using the null to null criteria. And this is nice and intuitive and fairly easy to use, because if you had to resolve some signals, typically as an engineer you're not going to start thinking, can I resolve a signal that's at 3 pi over 10 and between that and 2 pi over 10? No, you're never going to think that. You're going to think, I need to resolve a signal because I'm building a sensor or some kind of instrumentation, and I need to resolve a signal at 250 hertz and 260 hertz or something like that. How do I do that? How long do I have to sample and collect data before I can do that? And this is where you'd use a simple thing like that to help kind of move you along. I think we can do an example. So, bottom line, we can think about this in terms of continuous time. So, time support tau, which I'm calling it time support, and call it collection time. Determines frequency resolution. So if we end up with, in your mind's eye, you want to be able to think of this as I'm collecting some data over some time period. And I think the easiest way to think of it is I put a window on it, because this signal could be infinitely long, but I only collected from here to here in time. So that's my time support. Well, when we start playing our games in frequency, that time support has consequences in the other domain. It basically means that when we go into the frequency domain, this null to null limit is now 2 over tau. Where that's in hertz, this is in seconds. So let's just do an example where we're just going to think through using this intuition. So we're going to collect samples for 0.5 seconds. So if we do that, our time support 0.5 seconds. So frequency resolution, and this is the null to null, of course, is going to be approximately 2 over tau, or 4 hertz. Now notice I didn't say how fast I was collecting the samples. And I didn't because it's irrelevant. It doesn't really matter for the most part. Maybe if you collected one sample, you could say, aha, not good enough. But as long as you, it's not really a factor. It's mostly the time support. So if you can collect enough, if you can collect over this time period, you can do it. So if you needed to resolve signals that were 4 hertz, you could go backwards and say, I only need to collect for half a second. Now, in a lot of applications, time is very important. If you're doing something over here, you can't do something over there. If you're collecting samples on this comm channel, then you can't collect on that comm channel. If you're a radar and you're scanning over here and you're integrating and you're collecting this data over here, then you can't be collecting data over there, and your surveillance rate drops. So this isn't really a free thing. It's not free. So that brings us to our next thing, which is, well, this was the frequency resolution null to null. What about the 3 dB? Well, the 3 dB criteria, and we'll write that out. 3 dB resolution is approximately equal to 1 over tau. In hertz. So what does that tell you? That tells you if you collected samples for half a second, seconds, then tau is 0.5, and that implies your, we'll call it del F, delta frequency or frequency resolution is what, 1 over tau, which is now 2 hertz. And so magically, you collected for the same amount of time, and now you're at 2 hertz resolution. Well, how did you do that? Well, because you signed up for maybe a more difficult task of trying to resolve those 2 frequencies with some kind of algorithm, which, if I had the charts, if you're going to do 2 hertz, you signed up with trying to resolve these 2 guys that are this close with 2 hertz. If you signed up for 4 hertz, then you're signing up for trying to resolve these that are farther apart and easier to resolve. So those are kind of your 2 criteria. How hard do you want to work? Clearly, if you have your druthers, just integrate longer. Make tau bigger till you're done. If you can get away with this, you can make your life easy. Otherwise, you're here. So I think the last thing I want to do is kind of show an example in MATLAB. Let's see. And what are we going to do here? I'm going to use kind of a weird example of trying to resolve 2 signals. And let's just kind of go through this little real short M file. So I'm going to try to resolve 2 signals, F1 and F2. One's at 350, one's at 440. And the reason why I want to do that is because that's part of that phone dual tone or dial. It's the dial tone in a touch tone phone. If I could get the sound to play on this, you could hear the dial tone just by playing these 2 frequencies in MATLAB. But it's it's kind of a quick intro to what we're going to talk about in about a minute. So,
Those are hertz, right?
yeah, these are in hertz. So let's start from the top. I'm going to collect n samples, which is 8,000. And then I made this other variable n10, which is just n divided by 8. Or divided by 10, so that's 800. And then it's what? N divided by 50, so that's maybe 40. And n divided by 100, which is 80. Or, yeah, it's 80, so that would have to be double that. That'd have to be 160, wouldn't it? So I'm getting less and less time support is what I'm going to do. And then I get a number to NFFT. And then F sample, I'm going to sample at 8,000 hertz. Mainly because I thought I could play back on this system, but another reason is because how long does it take to get 8,000 samples if you're sampling at 8,000 samples per second? 1 second, right? So, ergo, I can get down to high frequency or high resolution. So we defined some axis. I'm going to do my plot my spectrums. That's that 20 log abs of FFT. I want to plot it against some frequencies, which is minus F samp over 2 to plus F samp over 2. Cap T right here, that's just our good old friend Cap T, 1 over sample time. F1 and F2 are our frequencies in hertz. The collection time, N times T. So how many samples do I have here? 0 to N minus 1, so that's a total of N samples times T. And so that's a vector of times. All right. So now we make our signal. So that'd be cosine 2 pi ft plus cosine 2 pi f2t, right? You can't get much simpler than that. And so I have my signal, and then I have a a version with less time support, right? So this one only has 800, that has 160, and the last one only has 80 samples. And now I'm going to take all those signals, and that's where I did the 20 log abs, FFT, FFT shift, FFT, and then I zero padded the FFT to be a fairly large FFT, just so we can kind of take a look at it. And I plotted the spectrum of the full time support, the whole second, versus the ones smaller and smaller.
What's that max?
Oh, this minus max one, that was me being lazy. I just put minus max of this entire thing, so nothing will ever be larger than 0. I got them all scaled to the peak of 0 dB.
Oh.
Because if you normally do that, the power or the maximum value out of that FFT is going to depend on the amount of data you put in there. And all these data links are different. So you'd have all these peaks all over the place and you can't really compare it. It's just an irritation. So let's run this, take a look at the plot. So as you'd expect, let's start with the blue. So the blue is 1 second. And you can see these are nice sharp peaks that are well separated. It wouldn't take a lot of effort to separate these two signals. 1/10 of a second time support, which is up in the corner, I don't know if that's as visible as I would have hoped, is in red. So it's slightly less data. The window is shorter. The green is the 50th of a second. Finally, the blue is, this blue, cyan blue, is 1/100th. Or I guess it's 1/100th of the data record, yeah, which is a second long. So, it's getting wider and wider, and it's going to be more and more difficult. Now, one thing I didn't show here is kind of the dependence on phase, which when I ran this a few times with a random phase, you get different answers. Notice this phase here, if I had to put a phase in here, it's kind of +0. There's nothing there. Well, depending on what that starting phase is, you can get different answers, and I'll show you. Because when you put 0 there, it kind of gets you a false sense of security. See, already just putting it a random one made the blue one much more difficult. Now you'd have to come up with an algorithm that's searching through data and looking for dips on the order of right at 3 dB, right?
Oh, the peaks, like the dark blue peaks, those are the ones we defined as like the 2 signals.
Yeah, so if I blow that up real quick, that better be close to 440? I thought it was 450. No, it is 440. 440 and 350, sorry. So there's the blue on one side, and I guess there's 350, yeah. Make sure it's good, it's in at 350. Well, let's take a look at a few things we've been talking about, like null to null width. Let's look at the red one. That looks fairly easy to measure. So I'm going to go up to this main lobe, this guy here, and there should be 13 dB side lobes if we take a look at it. 0's there. If we come down, we've got our 13 dB side lobes right there. It looks pretty close to 13. Minus 12.88. Also, what did we say the main lobe width ought to be null to null? Well, if it's 1/10 of a second, right, and if tau is 1/10 of a second, and 2 over tau would be what? 2 over 1/10. So that's 2 times 10, which is 20 hertz. Is it 20 hertz? If we click on that, that's about 340, 339.8, close enough to 340. That's pretty close to 360. 360 minus 340, 20 hertz. Pretty, kind of what you'd expect from the physics of it. And I chose the red one because it's kind of the easiest to measure.
How'd you determine the 2 over tau?
That was from all our pencil whipping stuff. If I can get back to that. This is where, if you believed our spiel about the main lobe width of these rectangular windows being 4 pi over n plus 1, then we went ahead and converted that back into this and said, oh, that was 2 over n plus 1t, and that's just a fancy way of saying how long does it take to collect all this stuff, which was tau. And so it was 2 over tau, because 2 over this, and so That's our null to null criterion. And so then the nice thing was we could just jump on paper. 0.5 seconds gives you 4 hertz, and then even on the screen here, the PC, you can do it at your leisure. You can generate any signal.
Can we see the time of the 0.5 second? Collecting sample or collecting time.
Let's see.
Time is it in the time domain?
You want to see what the signal looks like?
Yeah.
Let's see. Do I even? I think I used to have that. No, I got rid of it. So let's look at the signal. So here's that. Here's the original signal. And that's all 8,000 samples. Now if we hold that on, we can go ahead and plot signal N10, which is the one that's reduced by a factor of 10. So it should be 1/10 of the amount of data there. Let me zoom out. Let's zoom all the way out. Reset to, okay, good. I can believe that's about 1/10 of the whole thing. So if it's 8,000, this better be 800. Looks like it might be 800. Yeah, pretty close to 800 samples there. So what we did,
This N10 is divided by the 8,000.
yeah,
Right.
that's 1/10 of the. I guess the key part is when you're generating this data like I did, you have to know I sampled it at 8,000 hertz, and I took 1/10 of the amount of data, and I had 8,000 samples to start with, so I made my life easy by saying, okay, that's a second's worth of data. I could make it hard if I took a different number of, it'd be confusing to do it. But I mean, if there's any particular, question, you can kind of.
That's the time domain.
Yes, the time
8,000.
domain version of it. So hopefully that's not too difficult to show. I'm trying to think if we want. Is there any other questions? You want me to do any other examples of any concern about this concept? It's it's amazingly easy to do once I think hopefully you can see that it's not really a lot. It's not like thousands of lines of MATLAB to simulate this for yourself and see that yes, the physics work out. You can separate things by.
And this is our take-home final.
It's somewhat related.
Related. Okay. So this will help us.
Yeah, that's why I'm saying.
We should ask questions.
Yeah, that's why I'm fishing for questions because hopefully, I think some of the homeworks also would help because you need to be able to plot things, right? Because that's why MATLAB is useful. If you can't visualize it, then you don't know if it's right. So if you can plot it and you can see what it looks like before, you can see what your filter frequency response looks like. You can see what the filter or the data frequency looks like, the spectrum of the data after you filtered it, and you can kind of believe yes, everything's working correctly. And so I think
Just to figure out on the take-home exams, the filters are all visual filters, or
yeah, we're just going to be designing filters using the MATLAB toolboxes for the take home. Which I guess we can go ahead and start talking about that next. All right, so take home final. All right. Basically, I sent everyone a problem statement, and what we're going to be doing is playing around with the touch tone frequencies. So everything on your phone, when you push a button, it generates 2 frequencies, and this is the frequency lookup table. So if you press a 1, and I wish I could get the sound to work on this thing, then you could hear 1 or 2. You can generate these. I guess you can use sound SC command to play them, which is what I was going to do. So if you press the 1 key, it's the same as that cosine 2 pi 697 times t plus cosine 1209, 2 pi 1209 ft, or 1209 times t. Kind of like what I generated before, you could generate it yourself if you press the 1. So every time we push one of these keys, we get two cosines, right? So for an example, since we're going to be generating some filters and kind of playing around with this data, let's look at touch tone signal 1. And I plotted this here just so you kind of orient you. So if I press 1, I need to get 697 and 1209. Well, we have a plus and minus frequencies, so we end up with plus 697, minus 697, right? Minus 1209 and plus 1209. Okay, so far so good. What do you do with that? Well, the task is to filter the combination of signals, which is the touch tone 1 and 4, so that only 4 remains. So what would that look like? Well, we know what 1 looks like. Now we have to put 4 on here. Well, 4 also uses 1209, so imagine making this a little bit taller. But 4 also uses 770, so now there's going to be a 770 tone in here on this, right? So this will be accomplished by filtering out the 697 so that you only have the 770 and 1209, which is tone number 4, right? If we go back up here, tone number 4, 770, 1209. We got rid of 697. Well, how do you do that? Well, you're going to have to use a high-pass filter to do that, and that's why I say it'll be accomplished by, filtering out the 697, so you only have these left. So I wrote filter requirements on your instruction file. So the desired filter, I have what you need to use, and I also even have high pass or low pass in case it's not 100% clear. Hopefully it's 100% clear. I've been looking at this so long it seems clear, but I don't know what it looks like if you haven't looked at it before. So anyway, I'm telling you what kind of filter and whether it's high or low, and what the stop band attenuation is, pass band ripple. You all have a data set named after your last name on the canvas.
So that way we don't share answers.
Yeah, it's supposed to be a final, so you're supposed to do your own work, kind of almost like a test. Yeah, like a test. So. Yeah, we're trying to. Yeah, this is the end. So do your own work. That's why send me questions if you have questions about this.
Is it like 50-50 in terms of grading requirements? Or?
That's a good question. This is 50 points. I think it'll be close to 50-50. It may not be 100%, but it's going to be.
Big portion.
It should be a big portion. I wish I need to kind of put a bound on it, don't I? It will not be less than 25%.
Okay. That's reassuring.
Well, because you have to do some arithmetic and decide, do you really want to do this? And I want to help you make the right decision. So it will not be less than 25%. And there's multiple questions to this. So one of the questions, you'll need to know what FFT size is available to implement. Let's see, implement an FIR filter that would do the same thing. And that's not stated here yet because it's just telling you what FFT size is available. Because if you remember everything we talked about, you might think, I said Chebyshev filter, which is an IIR filter. Why do I care about an FFT size? Well, you don't yet, but you haven't seen parts A through F. Exactly. Yep. That's so. Hopefully, let's go to the outline. Now I put on here 2 files. One of them is a template file, which basically has everything in here that my answer does for my problem, which is the touch tone 1 and 4, filter out 1, so you've only got 4 left. And I want you to reuse it because I understand the layout, and I understand. I want it to be neat and understandable, so I provided you the graphics. So, part A, 5 points. Sketch the touch tone signal spectrums before and after filtering. Part of part A, identify the signal to filter out. So that's just kind of saying, okay, do I understand the task? Part B, sketch the desired filter frequency response. So that is, do I understand what sort of filter I need to build? Part C, write an M file that will design and implement the filter. M file must be operational. Key point, because I'm going to run it and look at it. Part D, 10 points. Plot the spectrum of the actual filter frequency response and the data after filtering operation. Another M file must be operational. Just paste the picture into the presentation, but you got to have an operational M file. So you should think to yourself, what am I going to submit for this? You'll probably have some .m files and a .pptx or ppt. I guess make it pptx because I think that's what this is, right? That doesn't say. It's whatever I put out here. The difference makes no difference except when I put into Canvas, it only accepts PPT, and you try to upload a PPTX, then it matters. Right? That's right. That would not be a fun activity. So maybe I'll just make it accept both. So let's repeat, and then now part E, repeat part C and D using the fir1 command. So that's where you just type in what the order of the filter and the cutoff, and it designs the filter for you and gives you the impulse response. And it uses a Hamming window. Not that it matters for you. You just put in a very, very short command, which you're going to see in a minute, and then tell me what your filter order is. The only parts of this that makes it of any interest whatsoever is, one, you're going to have to iterate to figure out what filter order you're going to need, unless you write a program which to do that iteration for you, but I wouldn't do that. I mean, I did that because I have to grade all these different ones, but I wouldn't do that if I were you. It might take too much time. And part 5, assuming n log n complex multiplies, and you're going to use an overlap save or overlap add, how many complex multiplies per output sample for your FFT size that you were given. So, kind of the same thing we talked about with the block convolution.
So part E, what we need to specify our type of filter, like high pass and pass.
Nope, because part E is you're going to use the fir1 command. Part D is the part where you probably should show that in part D and C. So let's go through and see how I answered it. And I just put this in here sort of as a placeholder. I think all our problems fit into this box. Again, TT1 plus 4, get out TT4. Find HEJ omega. So part A for me, I had a touch tone signal 1, I have touch tone signal 4. So this is the second page of that. I got 1 plus 4, I got these signals together, and I want to filter this out. Before filtering, after filtering. All right, pretty straightforward. So that all you have to do is change your numbers to match your problem. And some of you will have high pass, some of you will have low pass. I'm doing a high pass example because I don't think we did a high pass example in class at all because, well, it's all kind of the same, really. You're going to type low or type, if you looked at those tools, I think we mentioned you just put high in the command, which you're going to see in a second. So it's really the same thing. So part B, what is the high pass filter frequency specs? So you've been provided these graphics, so you can change them to what you need in your pass band, your stop band. And down here you have, I guess everyone has, not everyone, but there's different sample rates in the data that you all have, so that will impact your frequency
The
specs.
calculations, we have to do those back end as well. Or how much or calculations will be done? Or will it just be input into the MATLAB?
I think hand calculations, to calculate what?
Like W stop, is that a function of
You
MATLAB?
can just put in the code.
Oh, okay.
Right, I mean, you could highlight this and do eval. I mean, whoops. Yeah, I mean, your 4-function calculator can probably calculate W stop because you can just see how I did it, 697 times 2 pi over F samp.
Yeah.
And so use this as a template so that your work is understandable and it's already pretty much done. You just need to kind of fill in the template. Then it makes it easy on me and easy on you. So part C. So part C was we got to build this filter. So you need to make sure you understand the command. This was a Chebyshev type 1. And if you read the, I think the inputs to it, these have to be normalized to half the sample rate, right? So 697 normalized to half the sample rate gives you W1, W2. You need the ripple, the stop band, and you throw it into this Chebby Type 1 order detector, or what do you want to call it, order calculator. Right. So I think we did one of these in class, but you had some homework assignments using Type 1 Chevy chip. So you can do this experiment if you want. You can use it. Some students seem to like to use it. That's why I started using it. And it gives you N, which is the order of the filter, and a modified pass band. So then you go back to Chebby 1, which actually designs the filter, the A and B coefficients. You provide it with N, and these other arguments, and this time you put high instead of low in there. So how can this go wrong? Let's think it through. Well, notice W1, W2 are not the same, and they need to be put in a particular order. So don't mess up understanding what these all are, how these relate, W stop, W pass, W1, W2, and then you won't have any problems. And then if you want to filter the data, you can just use the filter command, BA, and then whatever your input data is. And so then you just plot the spectrum. I think I even provided some code here. You can use some of this code. It's not all of it. Your MATLAB code that's executable will have more than just this in it, because you need to be able to have the, how did you get, where did I put, like spectrum needs to be defined and everything else. But I wanted to put in an excerpt of the plotting stuff, right? So you can kind of see 0 to fs over 2 minus 50. So put it in hertz power so it can be seen that, yeah, this is working correctly.
What's spec?
Spec is spectrum. So I defined somewhere else. That's why I said this is a MATLAB excerpt ... because I had to define spec somewhere, which is 20 log abs FFT shift FFT of what? Of y, comma n FFT. That's that sort of thing.
Is that other diary going to be posted on Canvas? The one.
Yeah, I can probably. I think we already have
already
that.
on there,
It's already. Well, I don't know if it's already on there, but we already had that in some of the homework answers, right?
Okay.
I think that's already there. If someone has trouble plotting this, if you can't find it in the homework, but then again, this whole thing is out there. Let's see, is this on here? No, it's not on there. Okay, part E. Part E was the part with the FIR filter. So this is repeats part C and D, just using the fir1 command. So how do we do that? We're going to say, okay, how do we do that? I want to do a FIR filter and a high pass, and I want the cutoff to be at 0.1925, which is what, 770? I guess it's not the cutoff, it's the pass band. So 770 is what I want to keep, and this, is that right? Yeah, and this 697 is what I want to be gone. Well, notice, what are the arguments to FIR1? It's the filter order, which you don't know, this pass band, and then put high. If you do that, it will create an FIR filter that will make this nice red frequency response here. And this is nice because if we look at 770 and in our mind's eye go all the way up here, it's right at -6, which is what FIR1 does. And we talked about that. It gives you the pass band is at -6 dB. So if you're ever building one of these things and -6 dB isn't good, then just shift it back, right? Make it slightly, move it so that you're it is what you want it to be. But that's what they've chosen to have it built into MATLAB. But I made it, but the assignment is to don't change anything, just use the output of FIR. Right. So I messed around with it and found it was close to 136th order, so I have 137 coefficients. And it's good to show you that because I wouldn't want someone to be sitting around here trying 8, trying 9, trying 10. The filters are, some of these filters are higher order. I think in terms of the Chebyshev and elliptical filters, it's on the order of either 5 or 10, depending on your sample rate that you got. And so that means that you will have a filter order that's about what I got here, close to that, or half of that. So if you're going to start guessing start around 60 and start looking at your plots, right? Don't start at 4. You might not be going anywhere for a while. So it also helps to have a worked problem so you can see it. So part F, okay. Suppose we decided that putting 137 coefficients into a difference equation was for the birds, and we're going to use an FFT and join the the new century. So assuming an FFT is n log n, there's our complex ops, which is kind of nice because it's 10 times 1024. So Ford FFT, 10,240, no problem. The complex multiplies, and this goes back to the block diagram. Hopefully you're not hopelessly confused at this point, because we're taking the input data, taking an FFT. Off over somewhere else, we've taken an FFT of the impulse response.
It's the taps.
Yep, the taps, the impulse response, or whatever, to get h of k. Then we got to multiply x of k times h of k. Well, there's 1024 outputs, so we have to multiply them. So that cost me 1024 complex multiplies. Notice I did not include the cost of doing the DFT of h of k, because we don't have to do that over and over and over again. Do it one time and you're done. So these are kind of like constants. But once we've done that multiply, we've got to do the inverse FFT. So that's another 10,240. So the total bill, well, I guess we're not there yet. We're at the 1024 outputs. I'm using the overlapped save algorithm, the way I like to think of it. So you have the p-1 or aliased. So we get a weird number out, 888 outputs. So what's the total bill to do this? Well, we got to do a forward transform, a backward transform, and in the middle a multiply. So you tally it all up, 24.2 ops per output sample. And if you compare it, which I didn't ask you to do, to the this one, do I even say what the order is here? I didn't even say what the order is here. Would be a good thing to add the order. I think the order for mine was on the order of like 11. So that would be 11 A coefficients and 11 B coefficients. So it'd be 22. It'd be on the order of 22, 23, 24 coefficients. And so at the end of the day, it's about the same number of operations if you use the FFT. But you don't have to make that comparison. That's just for your information. And that's it. So hopefully this helps, and you can use this outline. It's on the page. You got the template. You got some of the code. Any questions or concerns about this? It's going to be due at 6 p.m. on Monday, so you got all week. So you can put it off to the end if you want, but you won't be able to work on it if you're at the final. So use your time appropriately there. All right. Any other questions? All right. If not, good luck studying, and I'll see you on Monday.
And you're available on email. Oh, Phil, you're available on email.
So actually, I don't know. I'm afraid this too. I'm afraid this
Included in the final example,
Need to know the terms like the passband and all that stuff. Need to understand the specs, but you're not going to be doing any, like we're not going to do any Butterworth filtering by hand or any of that stuff, or Kaiser or stuff by hand, because we're not going to use calculators. That would be too cumbersome.
So chapter 7 specifically will be covered by the
Yeah, the take-home exam covers the nuts and bolts type stuff.
about FFT. We have like one at last homework. That's what very well one.
Sorry I asked you.
16.16.
I think I've been the one that's super expensive.
No, you're not going to have to draw
I
that.
like it. It's super. I think
Don't
it's.
worry about it.
No, the thing I want people to worry about is those equations, the decimation of time, decimation of frequency, and memorizing a butterfly diagram is not required.
He's like,
It was hectic for me. I was trying to memorize it for 3 hours like last exam.
I know. Yeah, we're not doing that. I don't think that's value added. You can look those up, and I don't know. I just don't.
he's like,
I guess every professor has their own things what they think is
Yeah.
important. I don't think that's important.
Okay. Thank you. Thank you so much.
All right, Russ, that's today's.
Thank you.
All right, thanks. Good luck.
Sorry,
Let's see. Did I give you everything this time? Yes.
Do you have any episode for this week or?
I was going to hang out outside for a few minutes if anyone wants to ask any questions.